everyone. We are going to start today the 9th week of this course, and the topic that we'll cover in this week is complex variable method. You see, we have derived the governing equations, then we have seen over last 3 weeks that how that governing equations can be solved for different problems in elasticity. And the methods that we used, mostly the power series method, either in Cartesian coordinate system or polar coordinate systems. Okay. Now, there are some methods, there are some problems in elasticity. We will see that application of those methods that we have studied so far is slightly tedious, and therefore we need to look beyond the approach. The governing equations remain same. The equilibrium equations and then compatibility equation, also the using the potential, how that equations can be converted into a single equation, that concept will remain same, but the methods through which we solve those equations, we have to look beyond some alternative method, so that there are large class of problems can be solved. And here we have a method which is based on complex variable. Now, in this week, we will learn how to formulate those equations. We have done it. We have derived this equation in Cartesian coordinate system, polar coordinate system. Now, here we will learn how to derive those equations or rewrite those equations in terms of complex variable, and then what are the how to solve those derived equations. And we'll realize that the many complicated problems with complicated geometry will be easier to solve using complex variable method, which was otherwise difficult using the approach that we have studied so far. Now, being the first lecture of this week, today, okay, before that, there are two books is very important. One is the complex variable. Is details of the complex variable is given in book by Churchill, which is a very good book on complex variable, but the applications of those concepts in the different problems in elasticity is given in some of the chapters in this book, the second one, the mathematical theory of elasticity. Okay, so being the first lecture of this week, we'll spend some time today to just revisit some of the important concepts in complex variable. You have already studied complex variable in your engineering mathematics, also in school maths. We'll just revisit, we'll just briefly review those concepts today. Okay, so if we have, so we define a complex variable on a complex plane, which is if you have an x and y, then this is the complex plane, and we know that the complex variable z is written as is equal to x plus I y, right, where I is the x is the real part and the I is the imaginary part. Now, it can be also written in terms of polar coordinate system using r and theta coordinate, and this becomes r e to the power I theta, right, where r is essentially, if you can write x square plus y square, which is called modulus of z, and then theta is equal to tan inverse y by x, which is called argument of z. We know that, right? Then we have the complex conjugate z bar can be written as x minus I y, which is z and z bar are the conjugate of each other, and then r is related to r can also be written at z bar. So, these are the things that we know. Okay. Now, then some operations in complex variable, some algebraic operations between different complex variable. For instance, if you have one complex variable z1, x1 plus I1 and z2 is equal to x2 plus I y2, then z1 plus z2 can be written as, the addition can be written as x1 plus x2 and then plus I into y1 plus y2. The real part, they can be added together separately, and the imaginary part becomes separate. So, this becomes essentially, if we have all these algebraic operations, you see different algebraic operations, we already know this. Okay. Now, once we know that, let us now define how to how to write a function, represent a function in terms of complex variable. Okay. So, suppose z is a function, take a function, any function, suppose f z is a function of complex variable f z, and that can be, this is essentially is f of x plus I y, and this can be written as u of x y plus I into v of x y. So, u and v are the functions. U is called the real part and the v is the corresponding to the imaginary part. Okay. So, for instance, if we take a function, say f z is equal to, take any function, say is equal to say a plus z square, then it becomes a plus x plus I y square, and then which is essentially becomes a plus x square minus y square plus 2I x y. So, this becomes a plus x square minus y square and then plus I into 2 x y. So, this is u x y and this is v x y. So, any function, if we have that function can be written in terms of two separate functions u and v. We will shortly see what is the relation of u and v, what are the conditions that u and v satisfy for a function to be differentiable. We will see shortly those things. Now, similar to the conjugate, similar to z bar, we can also define the conjugate of complex function, and that is equal to f of, say, the conjugate of complex function, and that is essentially we can write is function of z bar. And if we, in terms of the same variable, we can write it u of x and y minus I into v of x and y. For instance, if we have to, if we take the same function a z, then this becomes what? This becomes a plus z bar square, which is equal to a plus x square minus y square, then minus 2I x y. Okay. So, this is a plus x square minus y square and then minus I into 2 x y. So, this is u of x y and this is v of x y. Okay. So, conjugate can also be written like the z itself, the variable itself. Okay. Now, this is now once. So, we have now next is, let us see what is the, now you see all these equations that we derived, that is derived in terms of x and y, right, or in polar coordinate in terms of r and theta. Now, here we have to derive the equations, we have to rewrite the equation in terms of z and z bar. So, what we need is, we need a relation. We won't derive the, irrespective of the coordinate system you choose, irrespective of the reference frame you choose, the governing equations remain same. Equilibrium equations, compatibility equation, the essence of governing equations remain same, but only difference is the how you represent those equations, right. Now, we represented those equations in last few weeks, we have seen in terms of x, y and r theta. Now, we need to represent those equations in terms of z and z bar. So, what we need is, we need relation between x, y and z bar. Let us find out that relation. So, what is that relation? You see, if we take any function f, is essentially, so take any function which is f of z, okay, which can also be written as f of x plus I y, right. Now, if we have to differentiate this function with respect to z, then what we have? Del f del z. Now, the same thing if we write here, then this becomes del f del z into del z del x, just the chain rule, and then the del f del z bar into del z bar del x. Please remember one thing here. You may say that z and z bar is, if we know z, then we know z bar. But here, when we write this equation like this, we are treating z and z bar For instance, if we take a plane, right? Now, in a plane, we have two independent basis vector, right? If we take a point in a plane, then that point, in order to represent that point, we need two bases, right? In a plane, in 3-dimensional space, we need 3 basis vector. Now, in Cartesian coordinate system, those basis vectors are along the x direction and then y direction, x and y. And if you take, say, polar coordinate system, the two bases are two variables through which we can represent a point, location of a given point, that is r and theta, right? Now, since r and theta are the independent variable, the bases need to be independent, linearly independent, then only it can be used as a basis, right? Now, similarly, x and y are independent. Now, here we are using z and z bar as basis to represent a given point, location of a given point, or represent something. Now, you may say, so z and z bar they have to be independent. You may say that z and z bar is not independent, because if you know z, you know z bar. But the properties required two basis vectors to be independent, we can prove that z and z bar satisfy those properties, and in a sense, we can take z and z bar independent two bases. And therefore, if we take any point, say if we want to take, if we know z and z bar, so x coordinate of any point, say x and y, so x can be represented as z plus z bar, half of this, and similarly y can be represented as half of z minus z bar. So, essentially we are just transforming the basis. Instead of x and y, we are treating z and z bar as our basis. Okay. And that is the reason we took z and z bar separately. Okay. Now, so therefore, so del z becomes what? Del z becomes del z del x. If you see that, del z del x become z is equal to x plus I y. Del z del x becomes 1, and similarly del z bar del x becomes 1. So, this become del z plus del z bar, okay, del z bar. So, similarly, what you can do is you can write del y, del z bar you can write. So, this become, you can also write del z bar, and if you do that, then this becomes the same way, this becomes okay, there is a small thing, it is not z, we are differentiating with respect to x here, therefore, it has to be x, okay, it has to be x, because that is, it has to be x, right, it has to be x, that is why it is x, similarly it has to be x. Similarly, if we take del y become del z into del y, del z del y, and then plus del z bar into del z bar del y. Okay. Now, if we do that, and then what we have is, finally, we have this becomes I, and this become del z, and then minus del z bar. Okay. So, this is the relation that we have right now. So, del x is this, and del y is this. Okay. Del y is equal to this. Now, if we solve this two, then we have a relation. We can show that del z is equal to, you can try this, del z is equal to half of del x. We will be using this expression I into del y, and then del z bar. But this equation is important, because this equation we will use to prove one, or to introduce rather, one very important theory in complex variable. Now, this is the expression that we have. So, this expression, what this expression tells us? This expression tells us how z bar is related to x and y. So, using this relation, we have a we can actually will be using these equations later to transfer this expression from to find out first the relation between u and v, the functions for real part and imaginary part. And then subsequently, we also will be using this equation to prove some of the important concept, introduce some of the important concept. Okay, so once we have this, the relation between del and z bar, now let us see what is the derivative of any function. So what we have done is, so far we know what is z bar, complex variable, we know what is the complex functions, what is the conjugate of complex functions, then we also know what is the relation between this differential operator with respect to z bar and the operator with respect to x and y. Now let us find out what is the derivative of any function in complex plane. Now suppose f z is a function, okay. F z is a differentiable, a single valued continuous function, okay. Now then the derivative of that function at z0, say f dash z, we know that you use the very first definition of derivative that we learnt, that is f z0 plus delta z minus f of z0 divided by z0. This is the derivative, right. So any function, if we take, if any function in complex plane, suppose this is the complex plane x and y, and this is any point, say that point is z0, this point is z0. So we take another point which is z0 plus delta z, and then this delta z needs to be delta z tends to 0. Okay. Now then what we have is this is delta y and this is delta x, right, delta z. Okay. Now, so if f z is a single valued and continuous function, then we say that this that at point, suppose this domain is represented by D. Okay. Now then this is the derivative of f at any point z0 in D, it exists. Okay. Then only we can say that it is differentiable at point z0 if it exists. Not only that, if it is independent of the fact that how delta z tends to 0, what it gives you, the delta z has to be, this delta z tends to 0, but how this delta z approaches 0, tends to 0, independent of that fact, this definition, this f dash z0 should exist. Okay. Now what it means, now let us write that expression. For instance, if you recall our del f dash z, f dash z is equal to what? It is del f del z, right. Now f is equal to, so this is del f del z. F can be written as u plus iv, that is what we have seen. So this can be written as del z of u plus I v. Okay. Now what was the expression for del z? If we recall, the expression of del z was del x minus I into del x minus I into del y, right. So if we substitute that, what we have, del x minus I into del y, there is a half here, and then we have u plus I v, right. Now if we just write this expression and take the real and imaginary part separately, then what we have is u del x plus del v del y, and then plus I by 2 of del v del x minus del u del y, right. Now what is now important here is, you see, now what is, you see here, your this is the expression of expression of f z. Okay. Now when I say that this exists irrespective of the fact that how delta z tends to 0, It means that this equation should be valid. If f is differentiable and single valued, then this should be valid for delta x is equal to 0 and allow delta z to approach to 0 along delta y line, and similarly if we take delta y is equal to 0 and allow delta z to approach 0 along delta x. So, irrespective, so this equation is valid how the combination of delta x and delta x plus I delta y approaches to 0, but it has to be valid if delta x is equal to 0, but delta y approaches to 0, delta x is equal to 0 and delta y approaches to 0, or delta y is equal to 0 and delta x approaches to 0. In both the cases, this equation should valid. Now, you consider the fact that when delta x is equal to 0 and delta y approaches 0, essentially this is derivative with respect to y, and when delta y is equal to 0 and delta x approaches to 0, this is essentially derivative with respect to x. It means that in both the cases, then if we take the in both the cases, this derivative should be the same. It means that this is important. It means that now let us first separate the x part and the x part and the y part. Let us first do that. So, half of del u del x and then plus I into del v del x, and then we have this is equal to your plus half of del v del y minus I into del u del y. Okay. Yes. Okay, that's fine. Now, it means what? When in the first case, you see what I said is delta z tends to 0. In one case, what happens that delta x is equal to 0 and allow delta y tends to 0, and delta y is equal to 0 and allow delta x tends to 0. Okay. So, this is derivative with respect to z, this is derivative with respect to y, this is derivative with respect to x. Then what it says that irrespective of the fact how delta z tends to 0, if that exists, then this should be equal to this, should be equal to this. Okay. So, this is equal to this is equal to this. If it is, then what happens? You look at this. So, in one case this portion will be the derivative, and in the second case and in one first case this portion would be the derivative. It means then the f dash z is equal to f dash z 0, that is equal to, or at any point if you take f dash z, that is equal to your the first case, the first one is this del u del x plus I into del v del x, half of del u del x plus I into del v del x, and that should be equal to half of let us see del v del y minus I into del u del y, del v del y minus I into del u del y, that should be equal to this. Okay. So, this was when delta z tends to 0, this was when delta x tends to 0, this was when delta y tends to 0. Delta y is equal to 0, delta x is equal to 0. Okay. And that is the condition. If that exists, then how it approaches to z0, how delta z0 is approaches to 0, whether along the x line or along the y line, irrespective of the fact, they should exist and they should be same, and therefore these all are same. Now, if they are same, then if you recall how we compare two imaginary variable, then we compare the real part and the imaginary part. The real part becomes, if we compare the real part, then del u del x is equal to del v del y, and the imaginary part is del v del x is equal to minus del u del y. This is very important. This is very important. Now, so you see, if a function, if f is if the D is the domain, if the D is the domain, and if Z0 is the point in D, then we have seen then what is the condition of derivative at the existence of the derivative at Z0. Now, if it is single valued and differentiable at every point in Z, every point in D, then we say, means this condition is valid not only at Z0, at every point at every point in D, D is the domain, then we say this function is called, in that case the function is called I use different color, holomorphic or analytic or regular, okay, or regular. The point where this condition, it is not differentiable, then this does not exist, then at that point is called singular point. Okay. Now, therefore, if it is holomorphic, analytic function or regular function, then this condition exists, this condition is true for every point in Z, every point in D, and we obtain this relation between u and v based on this condition, and therefore, if it is the function is holomorphic, analytic or regular, then this condition valid for every point. Okay. Now, this is called, this condition, this is called Cauchy equation. Okay. So, for an analytic function or holomorphic function or regular function, this Cauchy-Riemann equations is these equations are valid at every point in the domain. So, if a function is given to us and we have to check whether the function is holomorphic or analytic or regular or not, then what we have to check is, we have to check whether we have to write the function first in terms of u plus I into iv, and then check whether uv satisfy this relation or not. Now, this relation tells you another important story. Let us find out that. So, this relation is, so let us, okay, before that, if we have to write this expression, you can do this exercise in terms of polar coordinate, means the functions are written in terms of r and theta. Here we have expressed z in terms of x and y. If you express z in terms of r and theta, r e to the power I theta, then also you will get some relation between their real part, the function in the real part and the function in the imaginary part, and that relation will be, you can derive this, that relation will be del u del r. The same Cauchy-Riemann equations will be del u del r, that is equal to 1 by r del v del theta, that is the first equation, and the second one will be 1 by r del u del theta is equal to minus del v del r. So, this corresponds to the first one, this corresponds to the second one. So, the same, it is Cauchy-Riemann equation, but using r and theta, expressing z in terms of r and theta. Now, so let us, as I said, this equation, the Cauchy-Riemann equation, tells another important story. Let us find out that. Let us see that. The equation is, the Cauchy-Riemann equation, if you write in terms of say Cartesian coordinate system, this equation is del u del x is equal to del v del y, and then del u del y is equal to minus del v del x. Now, from that, if you differentiate this expression with respect to x, then we have del 2 u del x2 is equal to del 2 v del x del y. Similarly, if you differentiate the second equation with respect to y, then we have del 2 u del y2 is equal to minus del 2 v del x del y, and then if we add them, this and this, and from this what we get is del 2 u del x2 plus del 2 u del y2 that is equal to 0. And recall this is essentially del 2 u is equal to 0. This equation is called Laplace equation. And similarly, you can also show that del 2 v that is also 0. This is another important equation. So, u and v, if it is, so what we have, suppose of a function, complex function, which is written in terms of u and v, u is the real and v is the imaginary part. If that function is analytic or holomorphic or regular function, then u and v they satisfy Cauchy-Riemann equations. And another interpretation of that Cauchy-Riemann equation is that u and v both satisfy Laplace equation as well. This is the Laplace equation. Now, if you recall the solution of the Laplace equation, the solution of the Laplace equation is harmonic. Okay. So, u and v from this, since they are the solution of Laplace equation, they satisfy Laplace equation, u and v are the harmonic function. Okay. But if they are not analytic function, if they are not holomorphic at a given point, the singular point, these are not valid. Okay. For an analytic function and a holomorphic function, u and v are harmonic, they satisfy Cauchy-Riemann equation, right. Now, another important thing is, suppose you know u for a complex function, if you know u, v can be obtained by using the Cauchy-Riemann equation. So, u and v are also conjugate of each other. Okay. So, by knowing one function u or v, you can obtain the another by using the Cauchy-Riemann equation. Okay. Now, so what we have done so far is we have just revisited some of the aspects of complex variable. We have seen what is complex variable, how it is written in terms of x and y and r and theta. Then we have seen some of how the algebraic operations performed between two complex variable, two complex numbers, and then also we have seen how to express the complex function. And then also we have seen how to transfer the derivatives, the operators between two definition. One is complex definition, another one is Cartesian coordinates in terms of x and y. We have seen how these two operators are related to each other. Then we have seen what is analytic function or holomorphic function, what is the condition need to be satisfied, a function to be analytic function, and the condition is the Cauchy-Riemann equation, the u and v should satisfy Cauchy-Riemann equation, and the another interpretation of the Cauchy-Riemann equation is u and v both are the solution of Laplace equations, both are harmonic, and by knowing one, another can be obtained. That is why u and v are called conjugate function, conjugate to each other. Now, next class what we do? Next class we see very important part is the integration in complex plane. There we introduce the path independent integration. You recall in one of lectures we were discussing if the function is not simply connected domain, is the domain is not simply connected, then what happens? We will bring those kind of domain now, and then see how this complex variable approach help us to deal with those kind of domain. Okay. So, next class also we will continue with the review of complex variable integration in complex plane. Okay, stop here today. See you in the next class. Thank you.